follow that optically. So this is again spectroelectrochemistry by exposing the bismuth vanadate to different condition. You control the transformation time and control the amount of bismuth phosphate, and we found out that the hydrogen peroxide Faraday efficiency increases. So we shift the selectivity towards hydrogen peroxide for this. Of course, we want to go further than this 40%. Another option is try to get alternative oxidations altogether. So now, for example, we put glycerol into the system and we can oxidize it to make the hydroxyacetone, for example, or the aldehydes. The challenge with these reactions is that it has a lot of different options. So we can go to different product, and of course we want to control it into one that is more expensive or one that therefore you don't need to separate them afterwards. Our first contribution is try to look at the effect of the ions in the electrolyte on this reaction. First, if you don't have any glycerol, this is just water oxidation, there's really no effect of this ion, so we're performing pretty much the same. So this is bismuth vanadate again, by the way. However, interestingly, when we put glycerol in, these ions, the supporting ions gives a lot of effect, right? So potassium phosphate shows the lowest performance, whereas the chlorate or nitrate also gives the highest performance. Selectivity also shifts, so the glycolaldehyde selectivity increases as we go to the sodium nitrite. So this cation and anion types, for some reason, influences the glycerol reaction rate and stability. The current hypothesis is that we found that this trend matches quite well the trend of Hofmeister series, or this specific ion effect, from phosphate to sulfite to nitrate and chlorate over here. We don't know whether this is just a coincidence, but from this correlation right now, we hypothesize that if you have the ions that are more closer to here, the strong specific ion effect, the glycerol will tend to agglomerate and it will bond differently to the surface of bismuth vanadate. But again, this is just the hypothesis at the moment. Controlling selectivity can also be done with the light intensity, so we try to do that to tailor the product. So here we can change the light intensity. It turns out with bismuth vanadate, the selectivity changes. If at the lower light intensity we get more glycolaldehyde, at the higher light intensity we have more formic acid here. We did IMPS and EIS, and it turns out that the charge transfer rate constant and the surface hole density corresponds pretty well with this, correlates pretty well with this product selectivity. So we think with the higher amount of accumulations of holes, it's promoting for the higher electron transfer product, which is this formic acid. Okay, with that I come to almost the end, and this is the final thing that I would like to share now. How can we decide which reactions that we want to do? So for myself, it was driven by the fact that I got confused because a lot of literature, a lot of people in the literature are recommending doing this reaction, that reactions once we go to the alternative oxidation. So there's no one objective way to look at it. So the contributions that we had is that we tried to compile everything that people try to recommend as far as we can, right? And we try to be agnostic onto what is the energy that is required. So we just look at the economic valuation. So we look at the product price, feedstock price, as well as the market demand, right? And we plot them here for the different reactions, and from here we can already do simple analysis, right? Some of the things that, for example, some of the reactions that are proposed are actually having more expensive feedstock than the product. So then you already know that for these reactions, probably it doesn't make sense to do. You want to go for something that is at this higher margin region. Or if you want to look at the demand, if you're really more interested in the impact, you can also look at the market demand and market price. Of course, you want to go into this region, high demand, high price, but unfortunately we don't have a lot of them that is suggested. I guess that kind of makes sense, that it follows this line, right? So you have something that is either low price, high demand, or high price, low demand, because that's how our industry is making them. A simple comparative TEA shows us that for these two different types of chemicals, we may want to implement different strategy. For example, if you take chemicals from quadrant 2, which is high demand, low price, like your hydrogen peroxide or formaldehyde, we can do scenario analysis going from centralized production to decentralized productions and then the inclusions of multi-product. And it turns out that this is the net present value, so you want to have it as positive as possible. It turns out that for this type of chemicals, it makes more sense to do a centralized production and makes more sense to do more a focused single product. However, when you look at the chemicals that are belonging to the quadrant number 4, such as the hydroxyacetone, which is this one, or MBY, which is I think this one, we see that the decentralized option is actually making a lot more sense, right? So the decentralized multi-product approach better. So this is a simple analysis, but it just tells you that different implementation strategies would be needed for the different chemicals, and it's still not sure whether which one that we want to target. It would require different strategy. Okay, I end with the summary. So I'll show you the coupling of hydrogenation reactions with the PEC hydrogen production. And then we also investigated the photoelectrochemical water splitting at elevated pressure, and we started to explore different alternative chemical reactions. For example, the hydrogen peroxide, glycerol oxidations, and right now we're also looking at other feedstock that we can get from waste. I thank my group member at CityU and also before at the